Hello and welcome to this talk about SociTrack, a platform for autonomous social interaction tracking via wireless distance measurements. COVID-19 has affected all of us and called for unprecedented efforts to limit its spread. One measure to contain the virus, which governments around the globe have been enforcing, is social distancing. However, the specifics vary. From a suggested minimal distance of 1 to 1.5 to 2 meters, health agencies have proclaimed different suggestions on how people should behave. One of the primary reasons for this discrepancy is the lack of scientific studies on the subject. We believe that enabling long-term experiments on people's interactions in their daily life could provide the necessary facts for a more scientific approach to these health questions. But the demand for human interaction tracking is much broader. Among others, childhood development specialists are seeking a better understanding of the impact of physical proximity between caretakers and infants. Similarly, researchers studying workspace dynamics investigate methods to improve our everyday interactions in the office. Through automated systems that track the interactions of elderly people, we can further verify that they keep themselves in physical and mental shape. We are primarily interested in two features for social interaction tracking. The available measurement accuracy of spatial distances is a key metric. While many systems provide room-level proximity, many of the aforementioned application scenarios require a much finer grained resolution in the order of decimeters. On the other hand, the flexibility to move and still maintain data collection is challenging. Most systems can only operate in single instrumented rooms where infrastructure has been deployed, which is clearly not sufficient if we seek to investigate how people behave throughout their everyday lives. Various wireless technologies can be used to gather distance estimates, but none of them manages to cover the entire application space. Instead of focusing on a single technology, we have been investigating whether a combination of techniques enables us to obtain a solution that is both highly accurate without restricting mobility in any way. This presents us with four major challenges. We must first find a technique that allows us to acquire decimeter-accurate distance estimates at up to multiple hertz. Secondly, our solution must not rely on any external infrastructure and remain autonomous to enable in situ experiments. Thirdly, due to the frequent changes in positions of devices, they must constantly monitor their environment and quickly detect and join networks. Lastly, our solution cannot use technologies that require line of sight, as devices should be worn below clothing and should not fail due to obstacles. Ultra-wideband has demonstrated in the past that it can deliver precise distance measurements in a small form factor. However, it has been shown that these measurements can lack accuracy due to small-scale fading effects and antenna nulls. To avoid these errors, previous work has proposed to aggregate measurements over multiple antennas and frequency bands to achieve diversity instead of using the raw ranges directly. We demonstrate that this allows us to achieve a median error below 5 centimeters over various distances. To enable infrastructure-free deployments, the solution must be battery-driven and hence energy efficient. However, diversity ranging requires the exchange of many messages, and in addition, as devices must continuously monitor their environment and discover new nodes, the high energy cost of UWB impedes performance. We solve this problem by exclusively using broadcast messages, which allows us to reduce the number of messages to linear in the number of nodes. Furthermore, we avoid any probabilistic channel access and schedule all interactions to avoid idle listening. To enable efficient neighbor discovery, we use a second Bluetooth Low Energy radio, a technology that is perfectly suited to periodic listening and transmission. The dual radio architecture also allows us to solve problems regarding node mobility. In traditional networks, groups that move around tend to split apart and decay into many individual clusters. BLE allows us to quickly detect neighboring clusters and merge them to form a network where all interactions are measured. To permit multi-hop communication in such a network, we use synchronous transmissions to reliably exchange packets without having to constantly update and form links between devices, making SociTrack highly robust to node mobility. Lastly, it is essential that subjects are not repeatedly being reminded of the monitoring, as this can cause them to change their behavior. With our UWB-based time-of-flight ranging, devices can be worn how subjects feel most comfortable with, which can be below clothing and inside pockets. From an experimenter's perspective, the BLE connections can be used to connect with commercial devices such as smartphones and laptops and directly send data back home. We've been actively using SociTrack in the field in a collaboration with researchers which study caretaker-infant interactions. You can find a video demonstration in our full talk on YouTube. We consider SociTrack research-enabling research. We hope that our method of providing infrastructure-free, high-fidelity interaction tracking using a dual radio architecture opens up new possibilities for social scientists. You can find all our hard and software publicly available on GitHub. If you're interested in using SociTrack for your research, please contact us. Thank you.